Hi, welcome to Demystifying Math. In this lesson, we're going to be discussing the symmetry of polar graphs. Remember that a polar grid has a polar axis, which is the horizontal axis. It also has a vertical axis, which we call the line theta equals pi over 2. At the intersection of those two axes, we have the pole. What we're going to be doing is testing for symmetry, and our first one is going to be symmetry with respect to the polar axis. So with that one, we're going to be looking at any points on one side of the polar axis and reflecting them over the horizontal axis. If we land on another point on the graph, and we can do that for every single point on the graph, then the graph has polar axis symmetry. We're also going to be looking at symmetry with respect to the line theta equals pi over 2. In this case, we're going to take points and reflect them over that vertical line and find points on the other side of the graph that correspond to that. And again, it has to be for every point on the graph. The third type of symmetry that we're going to be looking at is 180-degree rotation symmetry about the pole, or what we call symmetry with respect to the pole. Now for those points, we're going to rotate them around 180 degrees and see if we land on another point on the same graph. We're going to start off with our polar axis symmetry. Our test for polar axis symmetry is to replace theta with negative theta. If that produces the same equation after you simplify, then the graph has polar axis symmetry. Let's start with this example. We have r equals 4 cosine theta. If we replace theta with negative theta, we get the exact same equation. Your even-odd identities will tell you that. So in this case, we do have polar axis symmetry. Well, let's look at a couple of points. Let's suppose that we let theta equal pi over 6. Then our r value is going to be 2 square roots of 3. If we then replace theta with negative pi over 6, we get the exact same value. Let's try a pi over 4. Pi over 4, the cosine of pi over 4 is square root of 2 over 2. Multiplying by 4, we get 2 square roots of 2. We're going to get the exact same output by putting in negative pi over 4. Let's take a look at our graph. Now, in my lesson on polar equations, we graphed 4 cosine theta, so you may want to review that if you're not sure how to graph it. But it is a circle centered at the ordered pair 2, 0 with a radius length of 2. Okay, since it's centered at 2, 0, we know that it's going to have symmetry with respect to the polar axis. But let's look at our points that we just found. We have in quadrant 1, we have 2 square roots of 3 and pi over 6. So if we have negative pi over 6, that's going to throw us over the axis and put us in quadrant 4. What you should know about the cosine of these angles is that they have the same value for the cosines. The sines would have been opposites, but the cosines are exactly the same. The same thing happened for the pi over 4. There is another way to test for polar axis symmetry, and that's replacing r theta with negative r and pi minus theta. So looking at our trig identities again, these would be exactly the same. Let's go ahead and look to see where our angles would be. Let's say that we had the angle pi over 6 that we're looking at. If we wanted pi minus pi over 6, then we'd swing over here to pi and take away pi over 6. That's going to land us at 5 pi over 6. Since we're looking at the cosine, which is the x values, the 5 pi over 6 would have the negative x value, where the pi over 6 would have a positive x value. So they would have the same value but opposites. So you see how your test says pi minus theta and a negative r, so we're expecting the opposite output. So let's look at pi over 6. We already know that the output is 2 square roots of 3 for r. And when we put in pi minus pi over 6, or 5 pi over 6, we get negative 2 square roots of 3, just the opposite as what we expected. So that's proving that we have polar axis symmetry. The same thing is going to happen with pi over 4. When we plug in pi minus pi over 4, or 3 pi over 4, we get the opposite for the r value. Let's go ahead and plot these points on our graph. Now what you should notice is that we ended up with the exact same points that we had before, but they're labeled differently. So here we're looking at 5 pi over 6, which is normally an angle in quadrant 2. But because we have a negative radius value, we had to go to the other side of the pole and come over here into quadrant 4. The same thing is happening with the 3 pi over 4. Normally you would be in quadrant 2, but because we have a negative radius value, we had to swing over to the other side of the pole into quadrant 4 and plot our point. So you can see how this is showing that you have polar axis symmetry, because now they're reflections of those points that were in quadrant 1. The next type of symmetry that we want to look at is symmetry with respect to the line theta equals pi over 2. That's our vertical line. And we're going to use the graph of r equals 4 sine theta. Our test for a symmetry with the line theta equals pi over 2 is to replace r theta with negative r negative theta, or with r and pi minus theta. Well, both of those will be true. So you can again go through your trig identities if you're unsure of these. Or you can plot points and try to figure it out. So let's go ahead and plug in a few points. Suppose we started with pi over 6. The sine of pi over 6 is 1/2. So 4 times a half gives us 2 as our r value. Now we want to plug in pi minus theta. So that's going to give us 5 pi over 6. And the sine of 5 pi over 6 is also 1/2. So we get a 2 out. The next thing that we want to do is plug in negative pi over 6. Now we ended up with negative 2, just the opposite of what we expected. Let's try it pi over 4. So we have 2 square roots of 2. And then what we want to do is plug in pi minus pi over 4, which gives us 3 pi over 4, and we have the same value. Let's try putting in negative pi over 4, and we ended up with negative 2 square roots of 2. Let's see how these look on our graph. So this time we have a circle centered at the ordered pair 0, 2 with a radius length of 2. So we have the ordered pair 2 and pi over 6 here. And it reflects over the line theta equals pi over 2 to become 2 and 5 pi over 6. Now the other one is negative 2 and negative pi over 6. So if we had started at negative pi over 6, that would have been in quadrant 4. But we had a negative r value, so we're going to the other side of the pole, and we get back to the same point, 2 and 5 pi over 6. So these are actually the same point, just two different ways of writing them. Our next type of symmetry that we want to talk about is with respect to the pole. And our test for this type of symmetry is to replace r theta with negative r theta, or with r and pi plus theta. If you get the same equation after you simplify, then you would have symmetry with respect to the pole. So I started off with some points here, and we'll go point by point to see what happens. So we're starting off with theta equals 0. So 2 times 0 is 0. So we still have 0 here for the sine. And then we want to add pi to our angle measure. So we're going to end up with an angle of 2 pi that we want to plug in and find the sine of. And that's still going to be 0. Next we're going to start off with an angle measure of pi over 12. Taking twice that, we get pi over 6. And then taking the sine of pi over 6, we get 1/2. For the other equation, what we want to do is add pi to our angle and then double it. So we're adding pi to pi over 12, so that gives us 13 pi over 12. And then we're going to double it, so we get 13 pi over 6. And then I found a coterminal angle with that one, and I got pi over 6. So we got back to the exact same angle that we plugged into the first equation. So we're going to have the same sine. Okay, starting with pi over 6, doubling it, we get pi over 3. Taking the sine of pi over 3, we get square root of 3 over 2. Now for the other equation, we're going to add pi to pi over 6 and double it. So that's going to give us 7 pi over 3. And then I found another coterminal angle with 7 pi over 3 at pi over 3. And the sine of pi over 3, of course, is square root of 3 over 2. Let's try one more. So we have pi over 4. Half of that is, double that, and you get pi over 2. And then the sine of pi over 2 is 1. Starting again with pi over 4, we're going to take pi plus pi over 4, which gives us 5 pi over 4, and double it, and simplifies to 5 pi over 2, which is coterminal of pi over 2, which is going to give us a sine of 1. So you can see by a point-by-point relationship that these two equations, sine of 2 theta and sine of 2 times pi plus theta, that are going to give us the exact same output values. So this graph has symmetry with respect to the pole. Now this is the graph of the equation, and it's a rose curve. We're going to look at it in detail in another lesson, but you can see some of the points that are on there. Okay, the other test for symmetry with respect to the pole is to replace r theta with negative r theta. So let's go ahead and try that. And what happens here is that you end up with a false test. But we already showed that it has symmetry with respect to the pole, and you can see that it does by looking at the graph. So what happens with these tests is that if you get a positive result, it is conclusive, and it definitely has that type of symmetry. But if you get a negative result, it's inconclusive. You have to go back and try another test or find another way to decide what the symmetry is for your graph. Now, by observation of this rose curve, you can see that it not only has symmetry with respect to the pole, but it also has symmetry with respect to the polar axis in the line theta equals pi over 2. So let's go ahead and test the polar axis symmetry. So we can replace r theta with r negative theta, or with negative r and pi minus theta. And neither one of those work. But you can still see from the graph that it definitely has polar axis symmetry, but both of our tests failed. So let's try the test for the line theta equal pi over 2. We're going to replace r theta with negative r negative theta, or with r and pi minus theta. And both of those are true for all points on the graph. So it has symmetry with respect to the line theta equals pi over 2. Well, if it has symmetry with respect to the line theta equals pi over 2, then if we take point A and reflect it over the line, we get to point B. It also has symmetry with respect to the pole, which we showed earlier. So that means that point B gets rotated and lands on point D. And then D is a reflection of A, so it must have symmetry with respect to the polar axis as well. So sometimes you have to go a roundabout way to show your symmetry on these. And that's happening because there's so many different ways to write the points on the polar axis, on the polar grid, that you may be missing it in some of your tests. So keep trying them and see if you can see some of the relationships with the symmetry. Thank you for tuning in to Demystifying Math.